Welcome everyone to the UEFI webinar. We'll be beginning the presentation shortly. Hello and welcome to the UEFI Forum webinar, Challenges, Solutions, and Benefits of Integrating Wireless Drivers in UEFI Firmware, hosted by the UEFI Forum. Our presenter today is Hemanth Venkatesh Murthy, a software senior principal engineer at Dell Technologies. I will now turn it over to Hemanth to begin his presentation.
Thanks, Samantha and Megan, for the introduction. Welcome everyone once again, and let's get started with the webinar. So the agenda for today is a quick introduction to UEFI and BIOS. Then we'll look at some of the use cases that need the wireless functionality in the BIOS. Then look at the challenges involved, as well as some of the solutions that have been implemented in Dell BIOS. So all of the solutions we will discuss have already been released, and they are available as part of the latest BIOS releases for the platform. And one thing to note here is the solutions and the use cases we will discuss are more focused towards client BIOS, which is the BIOS that is used for the personal computers, be it desktops, laptops, or the all-in-ones. So some of the solutions and scenarios, or some of the use cases and solutions could very well apply to other scenarios as well. But we will not go into too many details of other scenarios. Our focus of the webinar will be on the client BIOS. So a quick introduction to UEFI and BIOS. So UEFI firmware is part of BIOS and is responsible for the initialization of the system during power on, as well as resume from low power states. So BIOS is hosted on a dedicated flash device and is independent of the storage drive that is used to host the operating system. So BIOS is capable of initializing the system even if the storage drive is not present, because it has its own independent storage that is a flash device. So it's capable of initializing even when the operating system is not available. So this particular scenario is referred to as the bare metal scenario, where the operating system is either not available or not installed. And the talk focuses on utilizing the BIOS's bare metal capabilities to improve some of the service aspects. So serviceability is key for any OEM to ensure repair of in-field devices, and with probably providing a self-heal kind of scenarios where the systems are able to heal by themselves in the field, so that there is a minimum user intervention. So we'll be looking at some of the use cases related to serviceability and how the wireless functionality helps in those scenarios. So there are several scenarios where OS recovery is needed. It could be a corrupted OS, it could be a malware infection, where best option could be to reinstall the OS, or it could be because of hardware changes, the storage drive is replaced or the motherboard is replaced. So if the storage drive is soldered onto the motherboard and the motherboard gets replaced, so there will be a need to reinstall the OS. And the nearest IT admin these days could be hundreds of miles away. So it could be a stressful scenario for anybody and everybody. Even for a very tech-savvy person, it could be a really stressful scenario. So in those scenarios, BIOS is unaffected because it has its own flash storage and it's not dependent on the storage media for the operating system. So BIOS is unaffected, and BIOS can be used to recover the OS from by downloading it from the internet. So basically, kind of doing a self-heal of the system. If the OS is not booting, the system detects the scenarios and downloads the available latest OS, and then system recovers back to the original state. And Wi-Fi is the preferred option these days for most personal computers. And some of the laptops today don't even have the Ethernet port. So you need to either use a USB Ethernet adapter or a dock to enable a wired Ethernet connection. So having wireless functionality in the BIOS becomes mandatory in such scenarios. So just in case you are wondering what is BIOS Connect, it is a bare metal operating system recovery solution from Dell. So other scenario that we'll typically use the wireless functionality is the bare metal firmware update. There are several firmwares that are part of the platform. In addition to BIOS, it includes the embedded controller firmware, management engine firmware, and there are several others. These need to be regularly updated to ensure optimal performance and security. So although there are methods to update the firmware from the operating system, there are scenarios which require a bare metal firmware update. It could be a motherboard replaced in the field, and the service motherboard might have an older version of firmware and we need to update to the latest one. Or it could be the manufacturing process in the factory where the operating system is not yet installed on the system and we need to update the firmwares in the factory line. It could also be related to providing an OS agnostic firmware update for users. So a firmware update that is supported at the BIOS level doesn't depend on the OS. So, and the process remains the same whether it's the Windows operating system is installed or a Linux operating system is installed. And goal of the firmware update is to provide a seamless interface where the system is able to detect the right firmwares and the versions needed, downloads automatically from the internet and installs, so that there is a minimum user interaction required. And again, Wi-Fi would be the preferred connectivity for downloading the firmware. So we looked at the use cases that require wireless functionality. Let's start looking at some of the challenges. So if you look at, typically most platforms support either 32 MB or a 64 MB flash device. So compare this against terabytes of SSDs that are available for the operating system. So BIOS is already hosted in a very space constrained environment. And if you look at the wireless components that are needed, typically three major components are required for enabling the wireless functionality. One is the SNP Dixie driver, the supplicant Dixie driver, and the firmware. So all of these three components are chipset specific. So if there is an Intel chipset and a Qualcomm chipset, you will have one set of these drivers for the Intel and one set for the Qualcomm, as we can see in the snapshot on the right side. And The SNP driver interfaces with the network stack of EDK2. So EDK2 already has the TCP/IP stack and other upper layers required for the network connection, including the TLS driver, which provides the HTTPS connection. So once SNP Dixie driver interfaces with the IP stack, we can enable an end-to-end HTTPS connection over wireless to the internet. So what are the typical features we need to support? So we do need to support the latest security standards, including WPA3 and the latest Wi-Fi standards like Wi-Fi 6 and 6E. So there are a couple of different types of network environments that need to be supported. One is the personal network, which we typically use in the home environment, and the enterprise network, which is used in the office network environment. So the office networks typically have additional security requirements, including certificate-based authentication and others required protocols. So all of these components and features contribute to the size, and we see typically the size of one driver package could be up to 1.5 to 2.5 MB, and it varies from vendor to vendor. So in addition to the drivers itself, we also need to have application logic for voice recovery and FOTA. So all of these components contribute to the space requirements on an already space-constrained environment. So BIOS is already a space-constrained environment, and the challenge is how do we fit all of these features and components in the BIOS. So other typical challenge that comes up is related to platform variants. So OEMs typically support multiple variants of a platform. Could be a premium variant and a budget variant. These variants could have different vendor Wi-Fi chipsets, but they share a common BIOS. So what happens in such a scenario is that if there is an Intel chipset on one variant and a Qualcomm chipset on the other variant, so both of these will need to be integrated into the BIOS. So the SNP Dixie, the supplicant Dixie, and the firmware related to Intel, as well as for the Qualcomm, need to be integrated into the BIOS. And this could be extremely challenging given that a single driver package could be up to 2.5 MB in size. So other aspect to consider is the boot time impacts. So BIOS boot time is the measure of time taken for UEFI firmware initialization from power on till handoff to the bootloader. And expectation is to have the minimum BIOS boot time, and so that there is an optimal system boot time. So how do we ensure minimal BIOS boot time? By only initializing the components required for the operating system booting. So Wi-Fi controller is not required for HLOS booting and should be skipped during the UEFI phase. The Wi-Fi controller will get initialized when the operating system comes up, but in the UEFI phase itself, we don't need the Wi-Fi controller initialization. And the boot time, the last BIOS boot time could be viewed using the Windows Start menu, and every millisecond counts for the BIOS boot time. So the challenge here is that typically all components built into the BIOS get initialized during the booting process. So how do we come up with an architecture where we can skip some of the components like the Wi-Fi controller during the normal boot sequence? That is a challenge we need to address from a boot time perspective. So other aspect to consider is related to security. BIOS, as we know, is the root of trust of the system, and it hosts several certificates, including those required for a secure boot. So if the BIOS is compromised, the entire system could be compromised. And Wi-Fi connectivity should not become backdoor for attacks, network attacks. So there have been scenarios like the boot hole and pixie fail, and we need to prevent those kind of network attacks. So the challenge here is how do we prevent some of the network-based attacks like the man in the middle or denial of service, given the fact that all network security features available at operating system level might not be available at the BIOS level or at the UEFI firmware level. So given the minimal feature set at the UEFI firmware level, how do we ensure that network-based attacks are prevented? So we looked at the challenges involved in integrating the wireless feature. We'll start looking at some of the solutions that have been applied to in Dell BIOS. So one of the first solutions applied was to create a separate wireless region. So if we look at the BIOS flash map on the left-hand side, it mainly comprises of three main regions, the IBB, OBB, and the wireless FE region. So IBB is the ancient boot block, while OBB stands for OEM boot block, and typically two copies of IBB are maintained to ensure that if there is a corruption, the secondary image could be loaded, and similarly, mechanisms exist for recovering of the OBB. So the wireless FE region was carved out of the OBB. So the advantage is that the OBB drivers are all dispatched during the normal boot sequence. So carving out a separate region out of the OBB allows us to customize the dispatch of the drivers, so we can ensure that the wireless drivers are not dispatched during the normal boot sequence and are only dispatched on demand. That is when BIOS update of OS recovery is triggered. So this helps optimize the BIOS to boot time, and there are few other benefits as well that we'll look at in some of the further slides. So other interesting feature that has been implemented is to split the BIOS as a flash component and cloud component. So some of the UEFI applications required for OS recovery and FOTA are not really required for normal operating system boot, and those could be hosted on the cloud. And these are downloaded and executed on recovery, so on demand, basically when required. So, and the network connectivity drivers required for connecting to the cloud and downloading are part of the flash device itself, so that there is a seamless connection to the Dell cloud. So it has benefits of storage space optimization as well as boot time. Boot time, because initialization of the UEFI applications gets skipped during the normal boot process. And there is an added benefit of easy and quick upgrade of UEFI applications. So whenever a newer version of application is hosted in the Dell cloud, they get automatically downloaded and executed when OS recovery or firmware update gets triggered. So, and it does not really require a BIOS update of the systems in the field. So it provides a quick and easy method for updating the UEFI applications in the cloud. So once we have the cloud components, we do need to consider the security aspects. So it this slide kind of gives us an overview of what are the security aspects that have been applied in Dell BIOS. So the first aspect is related to flash protection. And there are several technologies that have been applied for the flash protection. They include the Intel BIOS Guard, RPMC, and trust chain. So Intel BIOS Guard is a technology that allows only authorized applications or authentic applications to update the flash device. So even if a malware gets access to the system, it is not able to update anything on the flash device because flash device is protected through Intel BIOS Guard. So BIOS Guard achieves this through a combination of PCH and AC RAM, which is authenticated code RAM. Basically, only authorized applications like the BIOS update application itself, the OEM application related to BIOS update itself will get access to the flash device. So other important technology used is called RPMC, which is the Relay Production Monotonic Counter, which is used for as protection against hardware attacks. So if the flash chip is desoldered and a new flash chip is soldered onto the system, so such scenarios can be detected using RPMC. RPMC creates a binding between the PCH and the flash device during the manufacturing process, and any replacements in the field will be detected and access restricted. So even if a new flash device is soldered on to the motherboard, the access is prevented through RPMC. And there is a chain of trust that is established between the various components of the flash device. So primary IBB is authenticated before loading, and the IBB authenticates the OBB, and OBB authenticates the wireless FE. So a chain of trust is established among the various components of the flash device. So when the wireless FE gets dispatched, so the drivers in the wireless FE region establish an HTTPS connection to Dell Cloud. So before the successful connection is established, a hostname verification process is run, which ensures that the server we are connecting to is authentic and the identity is established. So once the HTTPS connection is established after hostname verification, a catalog file gets downloaded. The catalog files basically provide details of where the UEFI applications are hosted in the cloud, in addition to other information related to the platform. So the catalog files, which are basically XML catalog files, are themselves signed. So the first thing the drivers does after downloading the catalog files is to verify the signature. So only after signature verification is completed, the further processing of the catalog files takes place. This is to ensure that there is no tampering of the catalog files. So once the catalog files are processed, the UEFI applications are downloaded into the DRAM. And the UEFI applications are also secure boot signed because they are being hosted in an external environment. So before hosting into the Dell Cloud, they get secure boot signed. And once they are downloaded into the DRAM, they go through secure boot verification process before the execution happens. So if again some tampering is detected in the UEFI applications, the applications get blocked. So once the applications execute, they continue their further process of downloading the OS image or the BIOS image, which have their own additional authentication mechanisms. So you might think, why so many security aspects are needed? This is basically to ensure a defense in depth. So even if one particular technology or feature has a bug and vulnerability and an attacker is able to bypass it, there are other technologies that prevent the attacker getting full access to the system. So basically, there are multiple layers of security that are built in to ensure there is a defense in depth and man in the middle and denial of service kind of network attacks can be prevented. So we looked at some of the solutions, and now let's start looking at what are the options available to host the wireless drivers. There are few options that can be utilized to host the wireless drivers and the packages. And we will look at some of those and also compare their pros and cons. So one of the easiest option is to use the ESP, or what is known as the EFI system partition. So most hard drives have a EFI system partition which hosts the bootloader files as well as BIOS configuration files. These could be used to host the wireless driver as well. So and these are loaded after secure verification, and this could be utilized for the wireless functionality in the BIOS itself. So this works as an extension of the BIOS itself, but there are few drawbacks of this approach, where the storage drive, if it gets replaced, the wireless features are no longer available because the EFI partition itself is in the storage drive. So once the storage drive is replaced, the EFI partitions are no longer available. So, and also the other disadvantage is that when the storage drive goes through a complete format, then again the wireless features will no longer be available. And typically, IT admins kind of burn their custom images onto the flash or onto the storage drives, thereby wiping the existing EFI partition and creating a new partition. In those scenarios as well, the wireless drivers are kind of lost. So, but it does have an advantage in the sense that the flash space requirements are reduced, since some of the drivers are hosted on the storage drive. The flash size requirements kind of get reduced. That's the advantage of this approach. The other approach is to host the drivers in the flash itself. So in this scenario, multiple drivers will need to be hosted in the wireless FE. Say if the platform supports three wireless chipset, so 3 driver packages will need to be hosted in the wireless FE region. So the disadvantage here is a larger flash space requirement, and but there is another disadvantage here, that if you need to add a new feature like the BLE support, the storage space requirements get compounded. The wireless chipsets are Wi-Fi BT combo chip. So if a particular platform is using an Intel chipset, so it will have a Wi-Fi driver package and also a BLE driver package. And if there are 3 different vendor chipsets being supported on this particular platform, we will need to include 6 driver packages into the wireless FE region. So the storage space requirements get compounded as we add new features. That is a big disadvantage of this approach. So, but it does support the bare metal scenarios, because all the wireless drivers are hosted in flash drive, and when the storage is replaced or unavailable, the features are still available. So it does satisfy the requirements of bare metal recovery compared to the previous approach of hosting in the ESP partition. It does not satisfy the bare metal recovery requirements. So let's look at a third approach, which is more optimal compared to the previous 2 approach, and does not have the drawbacks of the previous two approaches. So what we did in the previous two approaches was what is shown on the left-hand side of the diagram, which is to compile all the drivers into the BIOS ROM based on a BIOS configuration file. So the BIOS configuration file can indicate what are the chipsets supported for the platforms, and all of those drivers are compiled into the BIOS ROM. So at the compile stage, we do not have the knowledge of which platform the common BIOS is going to be deployed to, right? It could be deployed to the premium variant or it could be deployed to the budget variant. So we do not have the knowledge at the compile stage to make the decision. So both the drivers need to be included into the BIOS ROM to enable the wireless feature. But if you compare the approach on the right hand side, if you delay the decision of selecting the wireless driver from compile time to the flash time, so since the flashing process runs on each of the variants, so separate flashing process runs on the premium variant and the budget variant, even though it's the common BIOS, but the flashing process runs individually on each of the variants. So the platform configuration data could be utilized to detect what is the chipset installed on the variant and up and integrate only the required driver into the BIOS. This is basically what we call as applying the lazy algorithm. So how do we implement the lazy algorithm? Basically, by using the FMP driver. The BIOS flashing process involves several FMP drivers for updating the device firmware and the flash regions. So a new FMP driver was created to update the driver into the wireless FE region. So if you I think the important thing to note here is the primary IBP, secondary IBP, OBB, and the wireless FE region together constitute the BIOS ROM image. So what the FMP driver is doing is to do a partial update of the BIOS ROM. So there are security implications related to the verification of BIOS ROM, and those also have been updated to ensure this scenario is taken care. So if there are multiple platforms or multiple chipsets, I should say, that are supported on a particular platform, so all of those will be available as payloads in the BIOS image. Say a particular platform supports 3 chipsets, so there would be 3 BIOS payloads available in the image, and the wireless FMP driver can select the right payload based on PCI enumeration data. Since it is running on the actual platform, it can query the enumeration data to detect what is the chipset installed and pull the right payload from the BIOS image and flash it to the FE region using the BIOS card process. So, and the payload can include both Wi-Fi and the BLE drivers. So, we will need to include only 2 drivers into the wireless FE region compared to probably 6 that was required for the earlier scenarios. So, and it also satisfies the bare metal recovery requirement since the drivers are part of the flash image itself. So, and the manufacturing process has been updated to ensure that all the systems coming out of the factory already have the right driver integrated into the wireless FE region. So, in the rare scenarios where the Wi-Fi chipset is changed in the field, if the BIOS flashing is applied again, the latest driver will get integrated into the wireless FE region, and rest of the scenarios remain the same. So, and the end users do not have to worry about having to integrate anything related to the wireless FE. So all the drivers required are already burnt during the manufacturing process. So let's quickly recap the solutions and challenges we discussed. So how did we overcome some of the flash space constraints? Basically by offloading some components into the cloud, as well as applying the lazy algorithm, which ensures that only the required driver package is integrated into the BIOS ROM. And common BIOS for the platform variants are handled through the lazy algorithm, and a separate wireless region is a prerequisite for implementation of the lazy algorithm. The security aspects are handled through flash protection as well as cloud protection. Some of the technologies that are applied for flash protection include Intel BIOS card, RPMC, as well as trust chaining, while cloud protection involves HTTPS connection, hostname verification, signature verification, and secure boot verification. So boot time aspects are handled by, again, not initializing some of the components, which could include components in the cloud as well as in the separate wireless region. So since we separated out the wireless FE, those components can be skipped during the normal boots sequence, and these help optimize the boot time. So we have come to the end of the presentation, and thanks everyone for your time. We will try to answer as many questions as possible. Thank you.
We will now begin the Q&A section of the webinar. Our first question here is there any plan to support a wireless wide area network device in UEFI with a WWAN chipset provider?
So here some of the aspects to consider is the WWAN itself is not supported in the UEFI specification. So the Wi-Fi devices are supported in the UEFI specification. So specification does not define what are the protocols needed for WWAN. So, but from a Dell perspective, we have done POCs related to WWAN support, but nothing officially released yet, and that needs to be still planned out.
Our next question is, what is the minimum EDK2 release that would support the wireless functionality?
So EDK2 release does not come with the wireless drivers as we discussed. So the wireless drivers are supported by the individual vendors. It could be the Intel, it could be Qualcomm, Realtek, or MediaTek. So the wireless drivers itself come from each of the vendors, and all of the vendors do support UEFI wireless drivers. So rest of the network stack is already part of the EDK2 release, which includes the TCP/IP stack and TLS and all other drivers. So the SMP driver integrates with the UEFI network stack. So there isn't a minimum release that I'm aware of. The latest release do support the network functionality. But the wireless functionality itself is outside of the EDK2.
Our next question is it possible to have same BIOS supporting multiple Wi-Fi chipsets so that each Wi-Fi chip will have its own ACPI tables?
Yes, so ACPI, so once the Wi-Fi chipsets are integrated, so some of the ACPI tables also get integrated as part of the BIOS build process, and so those are available for query from the application side, OS, or from the OS side.
Our next question is, when you say Wi-Fi controller initialization is not required, does that mean Wi-Fi is not available at BIOS F2 or F12 entry point?
So what I mean is that Wi-Fi initialization is not required when we are booting to the Windows operating system. So when you are booting into the Windows operating system, you are not getting into the BIOS menu, which is either the F2 and F12. But when you get into the BIOS menu of F2 and F12, the wireless initialization does take place to ensure the wireless chipsets are integrated or detected.
Our next question is, can we customize the features that need to be initialized during boot time? Can we add or remove the features needed during boot time without rebuilding the BIOS image?
Unfortunately, that is not possible because wireless FEs are all part of the BIOS image. So we cannot uh, do a removing of the features without rebuilding the BIOS. So basically, whatever features go into the wireless FE region are based on the BIOS build time, because the FMP driver itself is also built during the BIOS build time.
Our next question is, how many vendors have provided drivers for UEFI runtime?
So all of the vendors we work with, including Intel, Qualcomm, Realtek, and MediaTek, have provided UEFI wireless drivers.
Our next question is, how will you fix issues related to performance considering that UEFI runs at single thread?
I think we haven't had too many performance issues because we are running on a SoC CPU which typically runs at gigahertz speed, and we are able to download more than 100 MB files in less than 5 minutes. So I think from a performance required at the BIOS level, so we are able to meet some of the customer requirements related to performance. So we haven't had too many challenges respect to that.
Our next question is, how is this different from Microsoft's CBMR solution?
So Microsoft's CBMR stands for Cloud Bare Metal Recovery. So CBMR also provides an UEFI application similar to SOS and FOTA that we discussed in the presentation. So, but CBMR does not provide any wireless driver or wireless driver integration into the BIOS, because that is the OEM responsibility. So CBMR is similar to the SOS and the FOTA applications that we discussed, and but there were a couple of disadvantages when we compared it to the existing Dell implementation, including scenarios where motherboard gets replaced. Those were much more complex to handle with the CBMR.
That's all the time we have for questions today. I want to thank you again for joining today's UEFI Forum webinar. The slides will be available on the UEFI Forum website, and the video recording will be available on both BrightTalk and the UEFI Forum YouTube channels. Thank you again.